We are now going to look at the electric field at a boundary between two different dielectric materials. We'll call one material 1. It will have an absolute permittivity of epsilon sub 1, and the second material 2 with an absolute permittivity of epsilon sub 2. We will define the angle of our electric field as the angle it makes with a normal to the interface between the two dielectrics. We can represent our electric field intensities as the sum of two components. One component that's tangential to the interface, and the other component, the one that is normal to the interface. Sub T for tangential, sub N for normal. By applying the two Maxwell's equations we have developed so far, we'll be able to get relationships for the tangential and normal components of the fields on the two sides of the boundary. The first Maxwell equation we will apply is the conservative nature of the electric field intensity, and we will see that will give us the relationship between the tangential components of the electric field intensity. For our path of integration, we're going to select a rectangle where two sides are parallel to the interface and the other two sides are normal to the interface. The tangential sides will be of length delta W and the normal sides of length delta H. It doesn't matter, but we'll select the distance from point B to the interface as delta H over 2, and for the interface to C as delta H over 2. Let's perform this integration. Let's start at point A and go clockwise around our path of integration. When we integrate from A to B, we get E sub 1 tangential times delta W. When we integrate from B to the interface, we're going in the opposite direction of E sub 1 normal, so the dot product between DL and E sub 1 normal will give us a minus E sub 1 normal times delta H over 2. Similarly, when we go from the interface to C, we'll get a minus E sub 2 normal delta H over 2. When we go from C to D, again we're integrating in the opposite direction of our electric field, so the dot product gives us a minus E sub 2 tangential times delta W. When we go from D to the interface, we get E sub 2 normal times delta H over 2, and we go from the interface to A, we get E sub 1 normal times delta H over 2. These terms here sum to 0. We can divide both sides by delta W. So the tangential components of the electric field intensity on the two sides of the boundary are the same, which means the tangential components of the electric flux density fields on the two sides of the boundary are not the same. Their relationship is determined by the permittivities of the two materials. To get the conditions on the normal components of the electric field, we're going to use a second Maxwell equation, Gauss's law. We know that in our dielectrics, we only have bound charge, but we're going to include the possibility of having free charge at the interface between the two dielectrics. Sometimes when this free charge is introduced, it's confusing because students want to think that all the fields are coming from this free charge at the interface. If you go back for a second to the situation without free charge at the interface, you have these electric field lines, but something's generating those electric field lines. And in fact, it's probably charge somewhere else. The Gaussian surface we're going to choose is one whose sides are normal to the interface and whose top and bottom are parallel, like this cylindrical structure we're showing. The tangential components of the electric flux density field go into the Gaussian surface and come out, so there's no net flux coming out of the side. When we integrate d dot ds over the top here, the outward direction of the surface is in the same direction as the normal component of the electric flux density field. So the integral of d dot ds over the top will be d sub 1 normal times delta s. On the bottom surface, the outward normal to the surface is in the opposite direction as the normal component of the electric flux density field. So the integral of d dot ds over the bottom surface will be minus d sub 2 normal delta s. And that's because the dot product between delta s and d sub 2 normal will have a cosine of pi radians in it, which is minus 1. And the free charge enclosed will be this free charge on the interface that's inside our Gaussian surface. So it will be the surface charge density times delta S. We can divide both sides by delta S, and we get our boundary condition for the normal component of the electric flux density field, that d sub 1 normal minus d sub 2 normal is equal to the charge density on our interface. For the case where there is no free surface charge at the boundary between the two dielectrics, so rho sub s is 0, the normal components of the electric flux density field on the two sides of the boundary are the same, which means the normal components of the electric field intensity will be discontinuous, that discontinuity being determined by the permittivities of the two materials. When the free surface charge on the boundary between the materials is 0, we found that the tangential components of the electric field intensity are the same on the two sides of the boundary, and the normal components of the electric flux density fields are the same on the two sides of the boundary. We can rewrite the electric flux densities in terms of the permittivities and the electric field intensities. From these right triangles, we can relate the tangential and normal components of the electric field intensities to the electric field intensities. For instance, E sub 1 tangential will be E sub 1 times the sine of theta 1, and E sub 2 tangential will be E sub 2 times the sine of theta sub 2. And E sub 1 normal will be E sub 1 times the cosine of theta sub 1, and E sub 2 normal will be E sub 2 times the cosine of theta sub 2. Now let's divide this equation by this equation. So the electric field intensities cancel. Sine over the cosine is the tangent, and we obtain the law of refraction for the electric field intensity across the boundary between two dielectrics.